Good afternoon. So today we are going to start our second part of uh, the transport and kinetics. That means we will mainly focus on the kinetics part. So in the past 1 month, we mainly deal with the transportation laws, diffusion, diffusivities, and ion conductivities, right? And from this week, we will finally move to the electron transfer part. So first, we are going to review what we have already discussed. Why we care the kinetics, because what we have mentioned before, that there is a very important concept called overpotential, which means that it is a difference between the potential that we measured minus the equilibrium potential. And the difference between that is called the overpotential. And to understand that better, you can also think about that is the excess-driven force from the external circuit that we should apply to electrochemical cell. And for example, in a lithium-ion battery, the black line, that is the open circuit curve, shows the equilibrium potential. But when we are passing the positive current or negative current, actually we get a deviation from the equilibrium potential, and both the blue curve and the red curve shows the overpotential, and one side is positive overpotential and one side is a negative overpotential, right? And why the overpotential is important, we have discussed many times, right? That will greatly influence energy efficiency, right? Because if we have the forward and backward charging discharging curve in not repeatable, not reversible, then we can not get all of the energy we put in the battery back. And the origin of the overpotential mainly arises from three sources: mass transport, electron transport, and contact resistance in batteries, right? And we have already discussed where are they come from inside the electrode, right? And then we have intensively study the flux equation, right? This is the flux density equation, and also the Faraday's law, right? Is a relationship between the current and the flux, and what is the flux influence? The flux is influenced by the aggregation, diffusion, and convection. And we have solved a lot of problems in the problem 2, the homework 2, and also the exercise, right? So now today we are going to start a new topic called electron transfer kinetics. And let's assume we have a homogeneous reaction. The reactant A go to the reactant B, right? And we will have two reactions. One is forward reaction, one is a backward reaction, right? And we assume that this is like our first order, means they are linear, depend on the concentration, right? And then we can draw the reaction flux R like this. R is equal to the forwarding flux minus the backwarding flux, right? And that is equal to the reactivity K times the concentration of reactant, right? And at equilibrium, we will have our net reaction equal to 0. So that means the forward reaction flux is equal to the backward flux, right? And the K is the equilibrium constant, right? Then it means when we put this term to 0, so if we put this term equal to 0, we will get the K, right? K is equal to the ratio between the forward reactivity divided backward reactivity, right? And we can get this expression, right? And this case, the delta G is the sum of different reactant species sums delta G. And next, we all know that based on the Arrhenius equation relationship, the reactivity is always relevant to the activation energy, right? And this is what we have already learned from the general chemistry. And another key is temperature, right? And we know that from thermodynamics, the delta entropy is equal to the delta energy plus the delta PV, and relatively equal to the delta energy, because most of the case, the pressure times V is a constant. Why? Because we said PV is equal to nRT, right? So the RT are constant, and N is the total number of materials. We have materials conserved, so PV's difference is going to be close to 0, right? And then we can redraw this equation to like this, right? First, this is equal to delta E, and delta E can go back to the delta H, and delta H can draw like this. And then we can like change the whole reactivity is relevant to the delta G, right? And when we mention the delta G, we may recall that, okay, we talk a lot of relationship between the delta G and the chemical potential, right? Delta G is the chemical potential. And also delta G is relevant to the potential, right? So that means we have a potential energy change during a reaction that, right? So that means we have a reaction coordinate, right? That means this is a reactant, this is product, and this is their relative potential energy, right? And it is typically like this. Between the reactant and the product, we have 2 delta G here, right? And usually we will have activated complex, right? So here, this hump is typically give us a barrier to overcome, right? And this is the delta GF, and typically it's like a formation energy. And this is a delta G, means this is if the reactions just go through the tunnel, it doesn't go through the barrier, right? And this is only the shortcut energy we need. That is typically the reaction energy, right? So that means the delta GB is a real like the biggest difference between the activated complex to the product, and the delta GRXN is what we will calculate from the NBS table. And the delta G formation sometimes is unknown because it is determined by what type of activated complex is, right? So this will influence greatly on what is over potential, right? Because the delta GRNX will tell us what? The U, right? We calculate the U theta from the delta G, right? So this is delta U. This is U, and what delta GF to us gonna be the eta, that is over potential of surface charge. And for example, most of you may have already heard one equation called the Butler-Volmel equation. And the Butler-Volmel equation is a very, very important equation, describes the electron transfer kinetics. And this equation assumes we have a reaction, one oxidizer plus electron turned to a reactant. And this reaction can go either way. There are 2 activation energies. One activation energy is the oxidation reaction, and another reaction is the cathodic reaction. One is anodic reaction, right? So this is similar to the forward and the backward, right? What is anodic reaction? Anodic reaction means we have oxidation reaction, means we have a backward reaction, and cathodic reaction means we have a reduction reaction, right? That means we have a forward reaction, right? So in chemistry, we cannot tune the delta G or delta H freely. However, in the electrochemistry, we have a different thought because the free energy and the voltage are directly proportional, right? Remember when we when we study at the very beginning, when we calculate the open circuit potential, this is the equation we are using to calculate the OCVE to the delta G mu, right? And then in this way, by applying the different potential, we can tune the Gibbs free energy, means we can tune the reaction driven force, right? For example, we have a reaction that is called the sodium gain 1 electron dissolved in the mercury. It will form a sodium dissolved in mercury, right? And once it is at equilibrium, right, these two reactions is equal, right? You can see, okay, is sodium and this is sodium ion, right? Assume their free energy is equal, so we will get two sides the same, right? However, if we apply a positive potential to the electrode, what's gonna happen? We have the right side lower than the left side, right? And that means we will have oxidation reaction. Why is that? Because of what? Because this reaction is easy to go from the left side to right side, right? So the oxidation reaction is easier, right? The reaction coordination is easy to happen from here to here. And on the other side, if we just tune the negative potential, then the equilibrium, right? And then we can shift the reaction from the right side to left side. That means we are driven the reaction equilibrium to the reduction region, right? And based on this above phenomenon, people have drawn the potential dependence on the energy barriers, right? So what is energy barriers? Remember, energy barriers is here to here, right? Because here to here give us the U theta, right? Is a standard Gibbs free energy change. But this region gives us over potential change. And when we are applying the different voltage, we will see the total curve, the standard free energy is shift parallelly, right? And that means we are changing our activation energy, right? If we have a zoom in at this region, we can see this is how the zoom in part look like, right? Because we have a cross B and a cross A, right? And this is like this is Fe minus E0, right? So this is E0, this is E, right? So we have applied one potential at E, and E0 is its original potential, right? The difference between that is the F times E minus E0, right? Because electron number is equal to 1, right? That is based on the reaction. The reaction is oxygen plus 1 electron turned to a reductant, right? So we only have 1 electron, so that NFE becomes Fe, right? So this is how we can see take a closer look at how the applied potential influence the energy, right? And we can see that, okay, it seems the total change is like this. This is total change. But what is important is the total energy change. We have two share. One share is 1 minus alpha F. One share is alpha F. And we will discuss more details why it's divided like this. But from the mathematics, we can see that, okay, the difference between this side to this side is a total change, right? But the difference between the B to A is 1 minus alpha. And the difference between B to the lowest difference is alpha F, right? So that means we have a share that part of the energy go to the forward, part of the energy go to the backward, right? And in order to have a better understanding of what is alpha, so here if we take a closer look at the two parallel line, and this is oxidation reaction line, this is reduction reaction line, right? Actually, we can put different angles here, right? Because these two lines are parallel, and the line R is crossing these two parallel lines. And we can see we have two angles here. One angle is called theta, and one angle is called phi, right? And we have a 2 theta because these two lines are parallel. So this angle is equal to this angle, right? And we may notice that, okay, we define the alpha is equal to the tangent theta divided by the tangent phi plus tangent theta, right? So tangent theta is what? Tangent theta is equal to this side divided by this side, right? And tangent phi is equal to this side divided by this side. So actually we want to know the contribution of the line that is increased and the contribution of the line that is decreased, right? So that's why this line is, this difference is called 1 minus alpha times Fe, and this distance, this length, is called the alpha times Fe because alpha is equal to this, right? So that means this change tells us, okay, we will have activation energy change, right? Previously, the activation energy is here to here. Now it is here to here. Okay, forgive me, I cannot draw a very straight line with my mouse, but you just imagine the activation energy is shift due to the parallel line is changed, right? And that is, if we draw the line, this is the difference between the two activation energy, right? Okay, and in electrochemistry, we define the alpha as a transfer coefficient. And the transfer coefficient is a very important coefficient that we use to measure the symmetry of the energy barrier. So what do we mean, the symmetry? So for example, if we have a reaction that the reactions is prone to happen forward and backward equally, then the alpha is equal to 0.5 or half. And if the reaction is prone to happen forward, right, from the oxidation reaction to the reductant, then that means alpha is smaller than 0.5. And if it is the other side, then alpha is larger than 0.5, right? So here I want you to have some basic idea, like why people are trying to develop some parameter like this, because alpha tells us a reaction naturally is prone to happen forward or backward, because it is not always it is equal to 0.5. And next, we are continuing trying to derive the Bartolomeo equation, right? So mathematically, like what we said, we have reaction flux, we have analytic reaction or catalytic reaction to for example, for the forward reaction or backward reaction, right? And then we will have some expression like this. And in this case, the delta G forward or like a delta G analytic, we can call that is equal to negative NF alpha, right? Because that is contribute to the forwarding. And on the other side, if we have the reaction that is catalytic reaction, we can say that the NF times 1 minus alpha. So remember, this alpha tells us the total share of the difference of how much energy, the total energy change is Fe, right? The total Gibbs free energy change is Fe. F is Faraday constant, E is potential, right? And 1 minus alpha tells us the which side? 1 minus alpha tells us forwarding, right? and alpha tells us the backward, right, share, right? So that's why 1 minus alpha, if alpha is smaller, then this reaction is going forward. And if alpha is larger, then that means this reaction is going backward, right? Okay, so by understanding this, actually, we are already very close to understanding thoroughly the Bartlett-Wolmer equation, because here R is the net rate of the reaction, right? And R is equal to the R anotic minus R cathotic, or forwarding minus backward, right? And we can draw the equation like this based on the share of the total energy change, right? And based on this, it seems we can derive something that is flux relevant, flux as a function of V, right? And in the transportation law, we know we have I is have a relation with N, right, or R, right? Because we already know that. So if we combine the two relationships, we will easily bridge the current to voltage, right? So that is the value of this Bartlett-Wolmer equation. So can we measure the V easily? So at equilibrium, typically the rate of forward and the backward are the same, right? And then what does that mean? That means we are reaching the OCV, the reaction potential of U, right? So assume we are at the equilibrium, right? And we are solving for the U, we can get a U is equal to this, right? And we can define the term. Another term is called surface over potential, like what we said. Surface over potential is the driven force for the reaction, and given by the difference between the actual potential drop across the electrode interface and equilibrium potential drop across interface U. So this is what we are mentioning, what is the surface over potential, right? And from this equation, we know that we can calculate the U, like based on the initial concentration and also reactivity K, right? And the over potential can be calculated by this, and U is already known, right? U can be calculated based on NBS table, right? And we also know the Faraday's law, right? We know R, and we know R as a function. We know R as a function of V, right? So now we can plug everything, right? We know R is a function of V. This is what we already get here, right? So we just plug the I into this equation, right? So now, and V is equal to the eta surface plus the U, right? So by arrange everything, we can actually write the total flux equal to this, right? So if we do some mathematics thing, we can put a lot of things like this is constant, and this is also a constant, right? So finally, we can draw the current as a relationship with over potential. So this is a very, very important equation, what I have drawn on the board last class. And this is called the Bartlett-Wolmer equation. The Bartlett-Wolmer equation gives us very, very important expression, how the current is relevant to the over potential. And because the open circuit potential is known, so that means we also know the I's relevant relationship to V. So we know both I's relationship to V and I's relationship to eta, that is over potential or the output potential. And one example, how we can use the Bartlett-Wolmer equation, or how we can understand that, is here you can see we have one coefficient that is called I0, and I0 has a name, is called exchange current. And exchange current tells us how fast one reaction can happen. And if the electron, the I0 is higher, that means this reaction can happen very fast. So for example, we and another parameter is called alpha, and alpha we have already mentioned that before, right? So alpha means is a transfer coefficient. And how to understand that? transfer coefficient, if we have a very smaller transfer coefficient, and we have a forward and backward voltage, right? And we can see we have a current of oxidation current, and we have a negative current of reduction current. Which side is happen faster? This side is happen faster, right? Because slope is steeper, right? And that means the oxidation reaction is hard to happen, but the reduction reaction is easier to happen. And if we have alpha is equal to 0.5, then we will have a symmetry, beautifully symmetry S shape, right? And on the other side, if alpha is very, very large, that means we have oxidation reaction, forwarding reaction super fast. On the other side, the reduction reaction, also the forward a backward reaction, very, very slow. So alpha's number tells us the reaction symmetry. So that is very important parameter we should know for the electron transfer kinetics. On the other side is the exchange current, right? Exchange current is I0, we see from the equation, right? And from the equation, we can say, okay, assume we have alpha, anotic and cathotic are both equal to 0.5, right? And then we can know that, okay, we have the exchange current that is super, super large. So the light blue give us largest current, right? Exchange current. And this is how the current curves look like, right? And the red curve give us the middle, right? And the blue curve give us the smallest current. So you can see for each case, the reaction is reluctant to happen when the I0 or the exchange current is very small. And when the exchange current is really, really, really large, then this reaction is super easy to happen. So you can also think about this as a concept of resistance. And people indeed use the exchange current to convert to the charge transfer resistance, because this is behave like a resistance behavior. And on the other side, we can take a look at this curve with the log file, right? Because the whole Butler-Volmar equation is in the format of exponential. In order to have a better look of what is going on, we can take the log on the y-axis, right? And versus the over potential of V, right? Then we can see how this is look like, right? So if we have a really large I0, we get really high, really, really steep slope, right? However, if the reaction is happening at a really slow rate, then, right, we will have a really like not that steep slope. And in the meanwhile, we typically calculate the interception to the y-axis here. We call that this interception is I0. If we do draw a line from here to here, this interception is called I0. So forgive me, I cannot write it super nice, but if you just take a look at Alan Bart's book on the chapter 3, they have a very detailed expression on how to derive the Butler-Volmar equation. And I hope we have more discussion on our Tuesday class. And lastly, how to use this linear and we call that Taylor slope behavior. So because we know that this is what already Butler-Volmar equation tells us, right? We have a mathematical expression like this, and we know that when we have the expression of exponential x, right? When x is super small, and we can do a approximation like this, right? And if we do this, that means we overpotential is super small. When the overpotential is super small, we can draw the I to this format, right? And then in this case, we can convert the exchange current to the charge transfer resistance, right? That's what I said. And Tarfield slope typically behave at a large overpotential, right? And when we have a large overpotential, right, we can do the like exemption. We can do the approximation to this format. The I is equal to I0 exponential minus alpha f eta RT. Why this side is gone? Why this side is gone? If we have really large overpotential. When we have a large overpotential, right? What does that mean? When we have a large overpotential, the larger of this side, right? And it will also influence the total, like the term of the larger the eta, the smaller this term, right? And then we'll also get a smaller term of this the first term, right? So that typically means if we have a larger overpotential, we can do the approximation from this term, the two term, to ignite to one term, right? And we can also draw the overpotential by taking the log of both sides. The eta is equal to the RT divided by alpha F line constant current minus RT divided by alpha F line I, right? So this expression is called the Tafel relationship. So I hope you can remember that, and we will have a homework relevant to that. And take a closer look at how to express or how to use the Tafel slope. So based on the expression of above, right, the interception is equal to the log I0, so we can convert it back. And the slope is relevant to the 1 minus alpha and also minus alpha, right? So these three, we can calculate just based on the curve fitting. And in the homework, we will give you some real data points so you can practice by yourself how to extract the Tafel slope by yourself. And lastly, we want to talk about the concentration and overpotential. So remember, we have already derived the flux in the relationship of this, right? Flux is equal to the forward minus the backward, right? Anodic minus cathodic, right? This is what we already got, right? And one more thing we should notice that is here we have a concentration term, right? We have a concentration term. If we want to convert it to the current, right? And we should consider the current and overpotential equation, because this term, when we have a non-steady state, when the concentration is time dependent, right? And then the concentration is not the same as bulk when we apply to a certain time, right? So then the Bartlett-Wolmer equation becomes the current overpotential equation like this. And the limiting current, we can calculate from this. And the oxidation concentration when at close to the distance to the electrode divided by the bulk concentration is equal to 1 minus current divided by the limiting current, right? So there is another format of the how to draw the current versus the current zero, how we can derive this the current versus limiting current versus overpotential. And one more thing, that in order to have a better idea of how the Bartlett-Wolmer equation is look like. So previously we have Bartlett-Wolmer equation, right? This is what we already know. Assume we don't have a time-dependent concentration, right? And we can extract the exchange current is like this, and hence we can derive the forward and the backward reactivity based on this, right? Because the K0 is standard reactivity, and K forward and K backward, and is a forward and backward activity, right? So by understanding this, we will know that if we have why we have a larger overpotential, we will have a larger current, right? But once we have a limiting current, for example, I divided by I limiting, we can achieve some curve like this. And this is the total current. This dotted line gives us only the cathodic current, only the anodic current, right? If we sum up the two dotted line, we can get this equal or the real current between that, right? So this gives us when we consider the concentration effect or the concentration dependent effect, we can have a combination between the electron transfer and the concentration transfer. Remember, if we don't consider the concentration dependent, what do we get? We get a current go to infinity high, right? And if we only consider the concentration effect, we will get a what? We'll get a flat line, right? Like this, right? And if we consider both, we get a mixture. It's like this curve, right? Okay, so lastly, I want just to have a brief summary of what we have achieved so far from the past 1 month. So first, we have already spent a lot of time on OCV, open circuit potential under the equilibrium time, and we want to know what influence the real output voltage, right? And then turns out that we realize, okay, there is a difference between the reality and the theoretical, right? That is overpotential. And the difference of the overpotential is origin come from surface overpotential, that is mainly come from the electron transfer, and the concentration driven overpotential, that is mainly come from the transportation of reaction, and the last is come from ohmic resistance, right? But this side can be measured, can be contributed by the IR compensation. This side can be like a predict from the transportation law, and this part, the surface overpotential, can be controlled by the Bartlett-Boehmer equation. So by knowing everything with hand, now we can say that we can easily understand how to control the current voltage curve. Okay, so that is all of the content I have for the electron transfer kinetics side. And I hope you guys can read the textbook along with this slide. And I will try to resolve if you have any questions on next Tuesday. Okay, see you guys. Bye-bye.